Hello and welcome. Today we're going to be talking about measures of center and spread. Now the measures of center are used to describe, go figure, the center of a data set. Some people will say the average of a data set. So an average that most people think of is actually called the mean. This is what most people tend to think of when they hear the word average. That's going to be the sum of all the data points, you add them all up, and divide by the number of points. It's also the sum of the distances between the mean and all the data points to the left is equal to the sum of the distances between the mean and all the data points to the right. Now that may seem a little bit convoluted, but all it means is if we have a couple data points and we would say the mean might be right here in the middle, if I were to find this distance and this distance and compare that with this distance and this distance, the sum of the green lines and the sum of the blue lines would be the same. And so the middle, where that purple line is, that's the mean. All right, most people just know add them all up, divide by the number of numbers. Now, the median is going to be the middle of an ordered set of data pieces. You have to put them in order from smallest to biggest first. The mode is the data occurs the most often. You can have multiple modes in a data set. And then the last one we're going to look at is called the midrange, the mean of the lowest and the highest values. It's very simple and very quick to calculate the midrange. I don't know of a lot of people that use it a lot. I'm sure there's some uses for it. But it's just kind of like a real quick way of finding a typical value from the data set. Let's calculate these 4 different types of averages for these given data sets. To find the mean, what we're going to do is actually add these all up and divide by the number of numbers. So the mean would be 21 plus 8 plus 9 plus 21 plus 28 plus 24 plus 11 plus 20 plus 12, oh man, plus 25. We add them all up and then we say, look, there's 10 numbers here, so we'll divide that by 10. I'll go to the calculator and get these all typed in. You can see I have 179, and then all I'll do is divide that by 10. Be careful, if I just hit divided by 10, notice that it's only the last number that's divided by 10. So you can either hit enter and then take 179 divided by 10, or I can actually just put a left bound parenthesis on there, and now it knows to do all that first, and then I can do divided by 10, and it will type it all in properly. So just be careful with that. That does get us 17.9 for our mean. The mode is the one that occurs the most often. And in this case, I can see that 21 happens 2 times, and I don't see any other repeated value. That means the mode is just 21. Do be careful, and notice that this isn't true, but if there were another number, say like a number 8 here, then we would have 2 number 8s and 2 number 21s, in which case we would have 2 different modes. It's okay to have more than one mode. That's not the case in this problem, but I did want to address that. It's perfectly fine to have more than one mode. The median of this data set is the middle point. And the first thing I have to do is to write these in ascending order. So let's get that done. All right, so I've arranged these in order from smallest to tallest, or from littlest to biggest, so to speak. And now what I want to do is to find the middle value. In a small data set like this, it's not too hard to try to find the middle. All we do is, I like to pair them up, and unfortunately it doesn't let me do this at the same time, but I would just put my fingers on both 8 and 28 at the same time. And then I would next put my fingers on 9 and 25. And I'm just going to keep working my way in until I get to the middle numbers. Okay, so 12 and 21. And then notice that I have these 2 middle numbers here, 20 and 21. Well, there's only one median, and the median is actually going to be halfway between 20 and 21. So the median would be 20 plus 21 divided by 2 does come out to be 20.5. Yes, your median can be a number that's not in this data set. 20.5 is just exactly halfway between 20 and 21. Lastly, the mid-range is what we get when we take the littlest number plus the biggest number and divide it by 2. That's 36 over 2, or 18. So now we have the mean, which we got when we added them all up and divided by the number of numbers. We also had the mode, which is the easiest one to find probably. That's where you just look for the ones that happen the most. Maybe the next easiest one to find is the mid-range, and that's just where you find the littlest plus the biggest divided by 2, right? That's the mid-range. And the median is not too much work if they're in order. If you have to put them in order, that can be a little bit harder. Next, I would encourage you to take a minute and go ahead and do these on your own while I do them. Okay. So the mean is just 18.4 for the mean. And the median, we have to write them in order first. Once they're written in ascending order, I can now find the median. All I do is start to kind of pair it off by like putting my fingers on 16 and 21, working my way in 17 and 20, and now all I have left is just 18 right here in the very middle. That's the median. That's our middle number. Okay. Now, these are several different types of averages, or what I would say like a typical way to describe the data set. So each of them are used different times. For example, the mean is used when each piece of data is weighed equally. We use the mean a lot, and it's probably the one you're most familiar with. It's not really useful when we talk about extreme outliers, though. For example, if I was talking about the people that live in my neighborhood, maybe we have like a teacher and they make $50,000, and we have a plumber who makes 80,000. I'm just making up these numbers, so I'm sorry if I'm way off. And then we also have somebody that works in sales and they make 100,000. And we have somebody else who works in, I don't know, electrical, and they're making 80,000, whatever. So if we have all of these, we could find the mean of the people in our neighborhood relatively easy. 50,000 plus 80,000 plus 100,000 plus 80,000. And then what we would do is divide by 4, the total number of people, right? So uh, the problem is you have to divide, not multiply. There. And we get 77.5. So the mean of the people in this neighborhood is about $77,500, right? And you'd say, yeah, that's a relatively typical amount for the people in this neighborhood. That number kind of describes everyone in the neighborhood. The problem is, what happens if somebody famous moves in and they're making, they make $50 million a year? Maybe an NBA player that decides to move into the neighborhood. And somebody that's making $50 million a year, whoa, what's going to happen here is I have to now take this, and I don't know if you noticed, I was doing these in terms of thousands. So 50 million is going to be 50 thousands, right? There we go. And then what we'll do is if we divide that by the 5 people now, notice we have this much bigger number. That's 10,062. And our new mean, now that we've had a famous NBA player move into the neighborhood that's making $50 million, the new mean is over $10 million. The problem is that's not a good typical number to describe the income of the people in this neighborhood. I mean, look, we have a 50,000, an 80,000, 100,000, an 80,000, and then 50 million. That 50 million is clearly an outlier, and we would say that $10 million is not a real accurate description of the people in this neighborhood. You see, when outliers are present, the median is a little better representation of the data set. In this case, if we were to line up our data and we had our 50, our 80, 100, and then our 50 million, which is 50,000 thousands, when we go and find the median of these sets, there and there, there and there, and right here, our median is 80,000. So 80,000 is a typical salary of the people in this neighborhood. And you'll notice that you would probably say, yeah, that's pretty representative of everyone except for that person. The person making 50 million doesn't really abide by that, but 80,000 is a pretty good representation of all the people in this neighborhood. That's why a median is pretty useful in a situation like that. You see, the median is resistant to outliers, meaning you could put in a giant number and the median doesn't really move that much. You see, before this famous NBA player moved into the neighborhood, we might look at this and we would say, well, our median was, here and here. Oh, these two in the middle. There we go. Our median before they moved in was $80,000. And then even after he moved in, we already found it was still $80,000. It didn't really change. That big giant outlier doesn't really affect the median too much. Okay, so when you have data sets that have outliers, a lot of times the median is a better descriptor than the mean. Now, the mode is useful when the highest frequency is the only thing that matters, such as in a vote. You only really care who wins. Whoever has the most, that's the one that matters. And then lastly, the mid-range only uses 2 data points. So that means you can calculate it very fast and it's very efficient to do, but it's not really a great descriptor of the set, especially when you have outliers. Okay, so we use mean and median pretty frequently. Let's continue to practice some of these. The next thing we're going to talk about is involving the median, and that's that any data set, we can split these up into 4 groups by first finding the median, and then you find the median of each half. So that should kind of make sense. I mean, if you wanted to cut something into 4 equal parts, the easiest thing to do is to first cut it in half, and then you would cut the lower half into halves and the upper half into halves. And what you've now done is created 4 equal sections, right? And so these are called quartiles. And each of these is a cutoff for 1/4 of the data. In fact, I'm going back. So, for example, this data right here, there's 25% of the data in that section. There's 25% of the data in this section here. There's 25% of the data in this section here, and 25% of the data in this section here. Now, if they're all 25%, then yeah, that's how we get our 100% of the data, right? So we cut the data in half, and then we cut the lower half in half and the upper half in half. Now, each of these end values, which, we said this was the median, if we divide these into 4 equal parts, we're dividing them into quarters. The number right here that ends the first quarter is called a quartile, all right? And then the number that ends the second quarter of the data, that median, that would be the second quartile. So I'm sorry, the first one is Q1, the second one is Q2, the third one is Q3, and so on, right? I shouldn't say and so on. That's really about it. Some people say the maximum value is Q4, but that's not really that common to do. We just call it the maximum. Okay. And then the percentile of a point describes how much data is below that point. And you can either say at and below or below. That gets a little bit picky, but I don't think you need to worry about it too much here because some people will argue both ways. Now, Q1 represents the 25th percentile because 25% of the data is below Q1. There's 25% of the data below that Q1. Q2 would represent the 50th percentile because if we look at all the data, remember percentile is how much of the data is below that value. Well, if this is 25% of the data and this is 25% of the data, then from Q2 and down, that would be 50% of the data. That's why that's the 50th percentile. And Q3 would represent the 75th percentile because once again, we would have all this data in here. And if we add all that up, then this would be 75% of the data. So that's the 75th percentile. Let's go ahead and work on finding these quartiles for a data set. The first thing we need to do, remember, if we want to find the median, they have to be in order. So I need to write these in ascending order. Let's take a minute and get those written out. Now that they're written in order, we're going to first find the median of the data. So once again, I like to take and just kind of pair them up, all right, until we get to the middle. Here's our middle, and we need the absolute middle of those. So this would be our median, or also known as Q2, and that would be at 36. The reason it's 36 is because we have to do 35 plus 37 divided by 2. That's the middle number. Then what we're going to do is look to the lower half of the data. Now to help us out a little bit, I'm going to cover up the upper half of the data so I don't get confused. It's pretty polka dot. And what I got to do next is to look at this lower half. So if I want to find the median of the lower half of the data, I would once again just pair up 35 and 31. And then we get to 31, 32. Well, the median of that is going to be our Q1, which is 31.5. We would get that by doing 31 plus 32 and dividing by 2. I do that because I have an even number of numbers there. Next, we'll look to the upper half of the data. Now we'll cover this up so we don't get confused by it. And I need the median of these 4 numbers. Well, just like before, those would pair up. We're finding the median of those 2. So that's going to be our Q3, which does come out to be 41. Again, I did that in my head, but I got that by doing 40 plus 42 divided by 2. So that's how we find our Q1, our Q2, and our Q3 for this data set. Chase is told that he's at the 75th percentile for height as a 9-year-old boy. What does that mean? It means that Chase is taller than 75% of 9-year-old boys. That's all. In a room of 100 boys that are 9 years old, Chase is taller than about 75 of them. So that's what it means to be at the 75th percentile. Now, we've done a lot of this just by typing it into the calculator and kind of manipulating it around, but Desmos actually does allow us to do some of this stuff using some of its functions. What we're going to do, while we could do this by hand, we're going to do it in the calculator by first pressing the plus sign in the upper left-hand corner and add a table. I do want to point out that I am using the Desmos graphing right now. And if you're on Desmos Scientific, you might need to download a new app to make sure you have Desmos graphing. Okay, if you're going online and just using the web browser, that's fine. Desmos graphing is what you need. And then you'll notice that I do have that little plus sign right there. So it's just to the right of that. I'll hit that first, and then I'll add in a table. Next, we are going to type the data entries into our first column. So I'll just hit 1 and then enter, and it moves it down. You can see this looks a little bit like an Excel spreadsheet or something from Sheets. Okay, I don't know why I have that there. Let's type them all in. Now that those are all typed in, we're going to go to the function menu and scroll to stat. The function menu is over on the right hand side of the calculator, and it's the fourth button up. So I'll hit the function button. You can see right there where it is. And then if I go down, you can see I have statistics right there. So we got to choose which stat we want to calculate. Well, I want to calculate the mean first. So I'll type mean. Whoops. You know what I forgot to do? I always forget to do this first time. I actually need to go to the next line because otherwise it's going to try to put the mean in that dot. So I go down to the next line. Now that I'm here, I go to function, go to mean, and you'll notice it's saying, hey, what am I taking the mean of? Like I wanted to do that whole list above. If we look up here, you can see that this list is named X1. The list is named X1. I want to find the mean of X1, so I will type in X1. This has now found the mean of that list, and it's just 6.6. These other ones on here, the median, yeah, we can do that too. Okay, we can come down here and go to function, scroll down to stat, and you'll notice the next one right beside mean is median. The median, I still got to find the median of list X1. And that's how I get 7.5. We could have done that by hand. It is what it is. We'll go to function. If I want to find Q1, you'll notice that quartile is directly below median on my list. Don't get that confused with quantile, which is right next to it. You want to hit quartile. We still want to do the quartile for X1, but notice that it has not given me anything yet. That's because this is like, hey, which quartile do you want? So what I have to do is, so I forgot this in the, we've got to type in a comma and then 1. So I'm going to hit a comma, and then I want 1, which stands for the first quartile, or Q1. In this case, that's 3. If I want Q2, all I'm going to do is hit backspace and put in 2. It's just a fast way that I can do this without having to retype in a bunch of stuff. So Q2 is 7.5, and I'll hit backspace 3. Q3 is 10. And I could do 4. Notice that it's 11. And think about that. It's calculating like where the fourth quartile would be, which is actually just the maximum value. That's all that is. And then let me get this back over here. The mode, Desmos doesn't really do the mode very well. There are some ways that you could go about doing this, but let me see here. One way that I'll just show you real quick is I actually just had a student show this to me earlier. I could do dot plot, and let's see if I can get this to work here. And there we go. Sorry, I got that typed in quick. Dot plot X1. So now what I've done is made a dot plot. You'll notice that it doesn't really show it unless you kind of mess around with it. The other thing you can do is to hit this little magnifying glass right here, which stands for zoom stat, and it'll kind of adjust the screen because sometimes it's hard to find. And all that we have now is you can see that here at the 10 is where we have the highest amount. The mode, the most often occurred, is 10. So if you have kind of a large set, this might be a way of being able to find the mode a little bit easier. So that's a kind of a nice way to do it. It's also just easy enough to look at your data set and say, look, I have 2 10s and I don't have any repeated values for any others. Lastly, the mid-range. Desmos does not have that as one of the functions, so I'm just going to do 1 plus 11 divided by 2. That's the min plus the max divided by 2, which gets me 6 for the mid-range. Let's move down and start talking about measures of spread. Oh, I know some people want those. So you type in a 2 for Q2, a 3 for Q3, and it doesn't really do the mode or mid-range very well. Measures of dispersion. Measures of dispersion are used to measure the spread of the data. There's 2 types. The range is the difference between the highest and the lowest value, and the standard deviation describes how much each piece of data varies from the mean. A small standard deviation means the values are in close to the mean on average, while a large standard deviation means the values are further from the mean on average. So let's just say for a minute, and I know this isn't in your notes, I just want to kind of give you a visual. If we have several people that took some tests, and they got a 42 and a 45, a 50, a 60, an 87, an 88, and two people got 94s. Well, their mean is 70. Okay. If I have another class and I had two people that got 68s, a couple of 69s, several 70s, a couple 71s, a couple 72s, their mean is also 70. So they're the same mean, but very clearly these are two very different classes, right? This first class has a lot of spread around. You can see it goes all the way down to 42 and all the way up to 94. In fact, the range of that data is uh, 94 minus 42 is 46. This data has a range of 46 points, whereas the range of the other data is only 4 points, right? Remember, range is a single number. It's the difference of the highest and the lowest values. And another thing to think about here, when you look at this second data set, all these data values are in very close together, right? Whereas the other ones are very spread apart. So not only is the range different, but just in general, they feel different. And that has to do with what standard deviation is. Standard deviation, if you can understand it well enough, it just probably the easiest way to describe it is it's the average distance the points are away from the average. Okay, let's consider this. If we look at how far that is, how far that is, how far this point is, how far that point is, and this point, and this point, and we find the lengths of all those lines, and we look for the average length of those lines, how far they are away from the average, that's actually, it's called something else. It's called the mean absolute deviation, or the MAD. But I'm going to tell you it's really close to what the standard deviation is. Standard deviation just kind of means how far you are away, how far each data point is away from the average. It's not exactly, but it's pretty close. And you could see that in this case, the standard deviation actually that I did on a calculator comes out to be 22.9. When we look over at this other data set, you can see that all of these data points are in pretty close to the average. There's very little deviation. There's very little movement from the mean. And so their standard deviation is actually only 1.3. A small standard deviation means the data is in very close and it's clumped together. There's not a lot of spread. A large standard deviation means that the data is very spread out. So that's just one quick example. You don't need to be able to calculate that just yet. Again, I am describing something called the mean absolute deviation, but if you can just understand that as a measure of spread, that's very close to what the standard deviation is. Okay, we'll explore that here a little bit more in a minute. Costco's in the market for a new line of tires to sell to its members, and Michelin is offering a new tire that lasts an average of 35,000, and a standard deviation tested for the Michelin tires was 10,000 miles. That means there's a lot of variation. Goodyear's offering the same style tire but lasts an average of 30,000 miles with a standard deviation of 5. Based on this claim, which tire is a safer buy for its Costco members and why? Well, I'm going to tell you right away, there's not one right answer for this, and I'll kind of tell you why. For this first one here, for the Michelin, we know that they're 35,000, and it says that the standard deviation is about 10,000. Standard deviation means like on average, how far are you away from that average? So we can create a range, and why don't we just do plus or minus 10,000? If we do that, this goes down from 25,000 all the way up to 45,000. So, if we go out one standard deviation, then these Michelin tires are lasting between 25,000 and 45,000 miles. If we look at the Goodyear tire, we can see that the Goodyear tire lasts an average of 30,000 miles, and it has a standard deviation of 5,000. So if we say plus or minus 5,000, then this goes down to 25,000 and as high as 35,000. So they both have a low end of 25,000 and a high end, well, wait a minute, the Michelin goes all the way up to 45,000. Okay, so it seems like if we just go out one standard deviation, that the Michelin tire might be the better buy. I know you said, but wait a minute here, you said there's not one right answer. Right, but what if we went out two standard deviations? If we took 35,000 and we went plus or minus, instead of 10,000, what if we went out uh, two standard deviations? We went out 20,000 miles. Now we're all the way down to 15,000, and then 35,000 plus 20 would be 55,000. You're like, hey, I'd love to have that 55,000. That's cool. But I don't want the 15,000. That's terrible, right? And if we look at the other one, it would be 30,000 plus or minus 2 times 5,000, right? So 10,000. Now we're going down to 20 and up to 40. I'm sorry, 20,000 to 40,000. So in a case like this, you can see the low end is 20,000, the high end is 40,000. Sure, I'd love that 55,000, but man, I don't want to go all the way to 15. That would be terrible. And maybe you want more consistency and say, I want to better predict where my tires are. So there's not exactly one right answer to this question. It's just something to consider. That's all. That's all we're getting at with that question. The next thing that we're looking at here is to calculate the standard deviation. This formula looks a little bit complicated. When we look at this formula though, X bar is the mean. So what this says is take some data point and minus the mean, minus that X bar, then you take that whole quantity that you got and you square it. The next thing that you'll do is you do that with every single one of the data points. If you have 10 data points, you've got to do that 10 times with each one data point. Then you're going to add that together. This symbol here is a sigma. It's a capital sigma, and it just means to add things together. After that, we're going to divide that answer by n minus 1. N minus 1 is the number of data points minus 1. Once you get that all finished, that's when we're going to square root that answer. And that's how you calculate standard deviation. Let's do that. Okay, so I just described that whole process to you, but all we're going to do, so for those of you that like to fill in blanks, is we're going to divide the total of the last column by n minus 1, and then we're going to take the square root of that quotient. Got it? Good. Let's do it. The first thing we have to do when we have a data set like this is to find the mean. So let's go ahead and add together all of that data. I'm going to clear all this out. And we're going to add together our data. Then we take our 72 and we divide that by 6 because we have 6 data points. So our mean is 12. Now that we know that, we don't need the calculator just yet. I'm going to go ahead and write the data here. 7, 9, 11, 12, 15, 18. Then we're going to write the mean all the way through here. And now I have to do this data minus the mean. So in this case, that would be 7 minus 12, and I get negative 5. 9 minus 12, and I get negative 3. I'll continue for all the data points. Then notice that it says data minus mean, which we did in the previous column, and now we have to square that. So I will take negative 5 squared. Notice that it's in parentheses. Negative 5 times itself is positive 25. Negative 3, quantity squared, negative 3 times negative 3 is positive 9. Once again, we do this for all of them. And then we're going to go through, oh, wow. Thanks for yelling at the screen there and telling me that's a 6, not a 5. Then we'll go through and add up all of those numbers. There we go, 80. I do want to point out that n in this case is 6. The reason that n is 6 is we have 1, 2, 3, 4, 5, 6 numbers, so n is 6. All right. As we continue to try to solve for standard deviation, it says the total from the last column, which is 80, divided by n minus 1, that's 5, because remember, n minus 1, that's going to be 6 minus 1 is 5. And then we have that square rooted. Well, 80 divided by 5 is 16, so we have the square root of 16. The square root of 16 is just 4. Our range, by the way, is the largest number, which is 18, minus the smallest number, which is 7. So the two measures of spread that we were able to calculate from this data set is a range of 11 and a standard deviation of 4. Now, good news is calculating the standard deviation is not something that we will do by hand very often at all. It's just obnoxious to do this by hand. So we're going to do this in the calculator, and just like before, we're going to put all the data into a table, and we're going to go to stats, and we use the standard deviation, STDEV. There is another one on there called STDEVP. We are not going to be using that one. That is called the standard deviation of a population. We don't want that one. Okay. So let's go ahead and we're going to calculate some of these statistics for this data set. This is the monthly rent values of a sample of several places in 2-bedroom apartments from 3 different states. I'm going to go through and do these one at a time. We'll do California first, and then Arizona, and then Indiana. So let's clear out our calculator. And now I'm going to go to table, and I'll just type in all of California. If you don't actually clear your table out, you might notice that maybe up here it doesn't say X1, maybe it says X2 or X3. That's totally fine. You just have to actually choose X2 or X3 or whatever it is when you're doing the calculations later. Because I deleted my tables out, that's why mine still says X1 here. So I'll get all my data typed in. And now that that's all typed in, I'm going to go through and I won't worry about the other data yet. I'm just going to find the mean. I'm going to do all 5 of these. So the mean, we go to functions, down here on statistics, and we type in mean. And remember, we've got to name this, so I'll put in X1. And that gets me the mean for California. It is money, so I'll go ahead and put that 50 cents instead of just 0.5. Next, I'm going to put in my quartiles. So function, quartile, and I've got to do X1, comma 1. There's the first quartile. And then I can back this up and do 2. That gets me the second quartile, which is also the median. And we'll do the third quartile. And then our standard deviation, so hit enter. We'll go to functions, and down here on statistics, you can see it says standard deviation. Mine is on the left-hand side right below max. So standard deviation, and we've got to do X1. I rounded to the nearest penny. And then also we've got to do the range. The range we get by taking the highest minus the lowest. So the range for California will be 5,200 minus 2,600. And that should get us 2,600, hopefully. And there's kind of our summary statistics of California. The next thing that I'm going to do is I'm actually going to go back up here, and I could put all of my data over here into Y1 for Arizona. And then I could do Indiana, I could put it over into the next one and call that maybe Z1 or something like that. I'm going to go through and change all these numbers though, just for reasons, I guess. So I'll delete all these out. Just hit backspace to clear out my data. There we go, it's all wiped out. And now I'm going to type in Arizona. Now that I have all my Arizona data points typed in, I'm going to scroll down here and hey, my mean changed. And so did my quartiles, and so did my standard deviation. See, all of those are just referencing the numbers that are in X1. And right now, I have Arizona in X1. So that's why I chose to retype all of these in X1 because I already have my functions put in here. Mean of X1 is 1778 and then round to the nearest penny. Down here, this is the third quartile. Make sure you make note of that. So I'll just go ahead and type and get that one put in here, 1875. But I can go back up and edit this and I'll put in 1 for the first quartile. I'll put in 2 for the second quartile, or the median. And then for the standard deviation, there's that one. You can see this has much lower standard deviation than California. That means there's a lot less spread. Now the range, remember we had to calculate that one by hand. The range for Arizona was just 2,000 minus 1,600, which is 400. I've got to do this again for Indiana. So I'm going to go up and clear all this out and just put in the Indiana data. There may be a better way to do this. I gotta be honest, I don't do this a ton with Desmos. I use some other software, but Desmos is free and it's slick. So get it all typed in and get it done. Now that that's all typed in for Indiana, I'll just go through and write down my numbers for the mean, etc. There we go. Now we have each individual state. Lastly, to do all the states, unfortunately, you actually have to type all of this in. Okay, so let me get that all situated. I already have Indiana all typed in, so I'm just going to go back and I'm going to type in the California next, and then I'll do the Arizona after that. So I already have Indiana. Now I'm going to type these other two states in. All right, I think I got them all typed in okay. If I fat fingered one of them and I just have wrong numbers, I'm real sorry. But the overall mean of all the data then, because I just didn't even realize that California was that big. For the standard deviation. There we go. And then lastly, the range, we're going to take the absolute highest number, which is 5,200. That's the highest rent anywhere. And then the lowest rent anywhere is 4,100. Sorry, is 1,100, which is a difference of $4,100. So you can see the range tends to vary a lot, right? That's because it's only using 2 of the numbers. Okay, so the range isn't always the best thing to talk about when describing a data set. Which state shows the greatest variability in rent prices? The greatest variability means that we're looking for the largest standard deviation. And in this case, the largest standard deviation belongs to California. That just means that you can find some that are kind of cheap and you can find some that are really expensive. Which measure of center represents uh, best represents a typical two-bedroom rent in each state? You know, this is really just kind of comes down to opinion, to be honest. If you have some outliers, if you have some data points that just seem like they don't really belong, then definitely choose the median. If you don't really have any outliers, then the mean is just fine. So it does kind of come down to a choice of just your preference. For example, in California, you can see that the mean is 3,400 and the median is 3,000. So, you know, I don't know, maybe the median, because you can find plenty of apartments that are, or two-bedroom apartments that are maybe a little bit lower. There's a very wide range of prices. So it's kind of a high standard deviation. I don't know that I see necessarily any outliers, any data points that really look extreme. You'll also notice that in the other two states, the mean and the median are actually pretty close together. You know, in Indiana, it's 1,247, 1,225. Those are both pretty close together. I think median in general works fairly well whenever you're talking about money. So which measure of center represents best for all of them? I don't know. Probably I'd just pick the median. And in fact, that's kind of one of the things that's typically advertised. Um, there's a lot of places that will say the median family house costs this much, or the median apartment. That's pretty typical. Compare the combined data set to the individual data set and what information is gained and what information is lost by combining all three. Well, one thing that's lost is the fact that Indiana is very consistent. I mean, it goes from 1100 to 1450. It's a very small range, right? The range is lost once you combine all the data sets. And the fact that the standard deviation for Indiana is so small, that's lost whenever you combine them all. Now, what's gained? Well, what's gained is a single solitary number. When you look over here for California, for example, or I'm sorry, not California, but you look at all states, you could say the median apartment or two-bedroom house is 1762. And that's just one number. There you go. And that's the median for all the states. And so simplicity, when you put it all together and you have just one number, cool. It's a little bit harder when you have to compare multiple columns and different things like that. So you do lose a little bit of that detail, but you gain some simplicity. Um, Also, the fact that California is so spread out, that has a large standard deviation. Arizona and Indiana both have very small standard deviations. Those are lost whenever you combine the data. So I know that's a lot, and I know this gets a little bit long. I hope you're able to get this figured out in Desmos. If I did make a mistake somewhere, I sure am sorry. Hopefully you guys caught it and were like, oh, silly, you fat fingered that number and got something way wrong. If so, let me know. Um, all right, well, good luck with this. Have fun in calculating some measures of center.